Can you believe it? It's not just a theory anymore. We know how to simulate a wormhole. In this video, I'm going to show you how.
Nobody has seen a wormhole. Nobody has produced one. Nobody knows if it is just a beautiful math, but without a physical reality.
Well, we'll take the world's best quantum computer and see if we can map that into building a wormhole.
And then it became just at the edge of what's possible.
We have two main theories that describe nearly all observable phenomena. These are quantum mechanics, which is the physics of the very small, pioneered by scientists including Niels Bohr, Erwin Schrödinger, and Max Planck, and general relativity, which is the physics of the very large, pioneered by Albert Einstein. Both these theories work extremely well in their two realms. They make predictions which can be verified and have passed just about all tests we've thrown at them. But the fundamental problem that still remains after over 100 years now is the lack of compatibility between these two theories.
So the story begins in 1935 when Einstein wrote a paper with Rosen where the first time Einstein-Rosen bridges appear. And these are bridges that connect two seemingly unconnectable pieces of space-time.
The idea is you start with a flat space-time, then you add something super heavy, like a black hole that breaks space-time, something that creates a kind of hole in the fabric of space-time because of a theoretical singularity which would occur at its center. It's a point of infinite mass density. Thus you get a kind of tube-like structure of space-time that ends up at the singularity. Now, if you have this same construction somewhere else in space, then you could just imagine these two tubes connecting such that you don't have a singularity anymore, but rather a tube that connects one space-time to the other space-time. This is a wormhole. It's like a bridge from one part of space-time to another.
We have this dictionary that relates gravitational phenomena to ordinary quantum physics.
You can tackle the same physics from these two different angles, and that's the most concrete paths forward we have in building a full theory of quantum gravity.
The physics of the black holes, we think is physics of quantum gravity, but we cannot send an experiment in a black hole and validate that.
So instead, we can ask, can there be quantum systems whose dual description looks like wormholes?
Where it gets interesting. What if the wormhole from the ER paper and the phenomenon of entanglement from the EPR paper were theoretically connected? What if two entangled particles very far apart were exchanging information instantly because they were intimately connected via a wormhole through which this information could transfer through space-time instantly?
Now I'm an experimentalist, so I look at that and I do, all right, what can I do about that?
We were thinking, we have the ability to do things in quantum in the laboratory. We're physicists. So could we imagine actually doing something with wormholes? It almost occurred to us immediately that we should be using the best quantum system that we know how to manipulate. And what is that? It's a quantum computer.
Quantum computers work thanks to entanglement. So this is the connection between them and wormholes. This does not mean that the authors created a physical wormhole in space-time, but rather, using a quantum computer, they manipulated quantum entangled particles in space-time that simulated the behavior of a wormhole. Now, the one thing I've been emphasizing is that this entire experiment, including creating the wormhole, was done in a quantum computer. So if you really want to understand the details, it would be important to know a little bit about how quantum computers work.
Quantum computers speak a different language than the ordinary language of bits. A bit, you look at it, okay, it's a 0 or 1, that's it. The correlations among qubits are richer and a lot more interesting than correlations among bits. It's this language of quantum entanglement. And so there's a world out there, this extravagant quantum world, which we just haven't been able to explore.
I've worked on a few projects at Google Quantum and got to get to know the device a bit. And the Google device is the best quantum computer that is around. All the magic happens in this little chip. You have the actual qubits as these superconducting pieces of aluminum, and that's where the entanglement happens. We had the access to the Google quantum computer. I came over with Maria and Daniel and Joe, and we were like, we have a proposal to try to, observe a wormhole on the quantum computer.
And to put the proposal together, it was obvious these are the people.
In physics, you have to have the courage of your own convictions, and you say, well, maybe it won't work the way that I thought, but we'll learn something by trying. And that's really the attitude we had going into this. I don't think we really thought it was going to work, but we thought we would learn a lot by seeing how far you could get.
They didn't say, you're crazy, let's do something else. They said, okay, you're crazy, let's do it.
At probably like 2 in the morning, I was running these quantum circuits. We're looking for a peak. That's the qubit making it through the wormhole. I'm watching the data as it comes out. There's a little bit of a noisy peak. At first, I was like, this is probably just noise artifact. But as the data kept coming and the peak kept getting clearer, it was like, this is a wormhole. I think I just saw one. And so I was immediately like sending it off to Maria and the others, like, I think we have a wormhole, guys.
He said, it's there. I said, no kidding, he's there. It was nuts. It was nuts.
Researchers said that in principle, if they had 2 quantum computers on opposite sides of Earth, a refined version of this experiment should be able to transmit quantum information from one side to the other. So, if this is shown to be correct, that could be quite profound.
What happens is
The qubits of the Google quantum computer are making a little bit of extra space, and that's our wormhole.
a pulse of negative energy falls into the wormhole.
Now the wormhole becomes traversable. It opens.
You put a qubit through one side of the wormhole.
The qubit is now in the interior of this wormhole.
That information will actually spread over the entire quantum system. This spread of quantum information,
It becomes shared by many particles in the form of quantum entanglement. And then, rather remarkably,
it has to refocus as a single qubit. And then, as the wormhole is closing, the qubit is exiting.
I was absolutely astounded. I thought we would get maybe a few steps towards a real wormhole and a real quantum computer. And I never really believed that we'd get all the way to something that was real.
Well, what Einstein said, he would have said ER equals EPR. I told you, I knew that in 1935. But he didn't.
I think this is concrete experimental evidence for ER equals EPR.
The vector is pointing right from the experimental point of view.
This is confirmation, a direct exploration of this connection between quantum entanglement on the one hand and the way space is knit together and holds itself together.
As Google builds more and more capable quantum computers, we will eventually be able to get this into a regime where we don't even know how to predict what's going to happen. And I think we're going to have hundreds of my fellow physicists now writing papers about all the other things you can think about doing now that we've sort of got this door a little bit open.
And as always in physics, when you are able to explore a new frontier, there will be discoveries that weren't anticipated. Just like when you build a more powerful accelerator to study particle collisions or a more powerful telescope to look at the more distant universe. A more powerful quantum computer will be able to study highly entangled matter that we've never been able to look at before.
I think in the next 20 years, there are going to be a lot of fun for fundamental physics. Being very close with quantum, we're going to learn a lot.
There's so many questions that one could explore using these ideas. And I think most exciting are the questions that we can't yet pose.